That's a good idea. Thanks for sharing. I will ask that you, if you have a regular question, thanks, Gerardo, for that. So he wants me to tell you all, I am the queen of partial credit, and that some points are better than none points. So even if you're turning these things in late, it's better late than never. And you're getting, hopefully you're going to be able to get some feedback on these assignments before your exam next week. I will tell you that lab content is largely not on your assessments. You will have a lab final, and we'll talk more about that in a couple of weeks. Your assessments starting next week and the last one, they are largely on lecture content. And so if you'll notice, I've prioritized grading things that build on the lecture content largely. So though this lab, this molecular geometry lab is a lab, it borrows heavily from the concepts that are in lecture and will be on your assessment. And so that's why it's a super big priority for me in terms of grading. I graded this explaining department scheme for those of you who have turned it in. So you should check for some feedback on that one as well, because we will be having net ionic equations on your assessment next week as well. That seems like a good segue, although I don't want to, I'm sorry, I'm sort of losing track of my thought. Oh, I know what I was going to say. Today I didn't build an engagement assignment. There's no Google slide document for you all to navigate to and copy. We're going to stick in the lecture notes. Today's topic is hybridization. I'm glad you're here today. I'm covering this completely differently than the book covers it. And so I will be assessing you based on how I cover it. And everything we talk about today will be on your assessment next week. Now, since I'm teaching it in a very different way than it's presented in the book, I'm giving you a homework assignment that's largely my creation and not what's in the book. So I'm not assigning you that much homework on this topic in TRO, because TRO makes different assumptions than I make. And so this practice assignment will be graded by me before your exam, if you submit it before the exam. And I will give you all the rich feedback, and all of these types of questions are fair game for your assessment. There's a third topic this week that is also asynchronous called molecular orbital diagrams. That topic will not be on your assessment next week. So there's one more lecture in this week's sequence that I'm not putting on this exam. Okay. That practice is due by Monday in order to get feedback before your exam. So I encourage you to get started on it after our lecture today, and just make some headway. It will be a submission on Gradescope. It is far easier for me to grade more quickly and thoroughly and fairly and give you better feedback through the Gradescope platform than it is for me to do the Canvas grader. So as much as I can put on Gradescope as a submission, I'm putting on Gradescope because it's just easier for me to get through the grading that way. Does anybody have any questions so far? Please put them in the chat or unmute yourself and let me know what you're thinking about. Okay, there is something else I wanted. Oh, next week you have an assessment. I will do the very same thing that I did last time, which is I will put, let's go back to what I did last time. Week 5. I will put a preparing for assessment 2 page together. And on that page, you will find the potentially useful information that you will be getting for assessment 2. You're going to have most of the same constants. I'm going to put Coulomb's law on your assessment, potentially useful information. And I'm going to change this periodic table to one that doesn't have the element name. So you do need to know those elements that I requested that you memorize before. You'll also be given a blank handwritten template. In that template, there's a little icon for everything that you're going to be recording yourself on. I ask you to put all of the recordings into a single recording. Don't make 2 or 3 separate recordings. Put them all in the same one. And ideally, you're doing this through Canvas Studio. If you'll remember, Canvas Studio is this little icon over here on the left. It looks like a computer octopus. You can do a screen capture through Canvas Studio, or if you're recording something on your phone, you can upload that through Canvas Studio. It's much easier for me to give you feedback through Canvas Studio. I do not want to have to download a bunch of movies like I've had to do for these past couple of assignments. I really want you to familiarize yourself with Canvas Studio and use Canvas Studio. To account for some of the bandwidth issues that some of you had in our last assessment, I'm going to make Canvas Studio, or the recording part of the assignment, have a bit of a later due date in terms of it won't be counted late if you submit it a little later, to give you that allowance for bandwidth issues. You should still not make a recording more than 5 minutes long, and that encompasses all of the explanations that you would do. Not 5 minutes for each explanation, 5 minutes total. I got a lot of you to grade, so I gotta be a little bit of self-preservation. I did try to give you feedback on your explanation for your last assessment with respect to when are you giving me too much detail and when are you not telling me enough. So please let me know if my feedback on your last assessment explanation was not clear and you want to know a little bit more about what I wrote if those comments weren't super clear for you. Okay, so as of Monday, you will have the blank template and you will have your potentially useful information. So you can print those out or whatever format you want to have them in order to complete your exam. The parameters of the exam will be the same. You will have the same amount of time to complete the written portion of the exam. And I'm going to extend the time for the oral portion just to account for bandwidth issues, not for the fact that it should take you that much longer to record it. Just that I want to make sure that you have enough time to upload it so that it won't be penalized. Does anybody have any questions on your upcoming assessment? I'm going to stop sharing this and I'm going to start sharing over here to give you a little bit better window. Ooh. Oh, I got to make myself host. Sorry. Rookie mistake. Where am I? Where am I? I'm on here somewhere. Here I am. Oh, I'm going to change there we go. Everybody can share. That's what I want to do. Okay, that's what I want to do. Okay, so with respect to your upcoming exam, I've outlined major topics that I think you want to make sure that you are aware of and prepared for next week's assessment. So there were some things that we had in week 4 that did not get put on your last assessment, and that were NIEs. Lots of NIEs. You've gotten some practice. There's even more practice available to you in a way to get extra credit on the exam if you submit those extra NIE practices by, Tuesday of next week. There were lectures in week 5, that week that we had the assessment, and those will be assessed. You will have solution stoichiometry on this. So I expect you to be able to solve problems with mass to mole stoichiometry and volume of solution and concentration into the mole tunnel. So using molarities as conversion factors. We then entered into a real long treatment of the energy of light and how that relates to atomic structure. We talked about electron configurations, and we brought it all together by having you explain some periodic trends. There are a couple of explanation practices that are still due on Friday for you to get some practice with those periodic trend explanations. One of them is just a written explanation of ionic radius. That's a discussion post. And the other one, the other periodic trend, you're supposed to have a conversation with another person about chemistry, and you're supposed to record yourself having that conversation about the periodic trends. So both of those, I believe, are now due this Friday so that I can get you some feedback before the exam. You will have to explain some things about the atom and atomic structure That's a much more conceptual, explain things portion of chemistry. And so you're going to have to write or use a verbal explanation on at least a couple of questions from these topics about the energy of the atom, Z effective, shielding, penetration, Coulomb's law, orbitals, all those things, explaining those topics from week 6. In week 7, that was last week, we really stayed focused. We learned how to do Lewis structures. We learned about this topic of resonance. We also learned about isomers a little bit, and we'll talk a little bit more about those today. And then we built into molecular shape, so VSEPR. So those are calculating that steric number and then determining based on the steric number, what's your electron pair geometry? And then thinking about invisibility, do you have any lone pairs? And so then what's your molecular geometry? And then this week, there's a lecture that you're largely supposed to do asynchronously about polarity. So after you know the shape of a molecule, you should be able to determine whether that molecule is polar.
Professor, can I interrupt real quick?
Sure, please.
You have a question in the chat.
Oh, thank you.
You're welcome.
Could you post these topics in the preparing for the assessment module? Of course I can, Kino. Thank you for the suggestion. That's a great one. So molecular polarity, that's an asynchronous topic that you will be assessed on for next week's exam. Molecular hybridization is the topic of today's lecture. It will also be fair game on the exam, although it builds into, and I'm going to cut the line here, molecular orbital theory, and this will be on assessment 3. This will be on assessment 3. So MO theory is the next thing that's covered in this module as an asynchronous lecture. There is, again, since I'm teaching it differently than your book teaches it, an extra practice assignment that's just on my type of problems and grading them in the way that I'm teaching these topics. And that will, again, be due to grade scope after your exam. So that practice will be due the Monday after the exam, I think. Okay. Any questions about preparing for the exam? Topics that are going to be covered. You're going to have quantitative calculations with stoichiometry. You're going to have conceptual questions about atoms and atomic structure and periodic trends. You're going to need to be able to deal with molecular structure. I was working with a student in an office hour, and I thought this was a pretty good moment that I had just to sort of talk through with that student about the logic of all the topics that have been in the last 2 weeks. The very first thing is to get yourself a Lewis structure. Once you have the Lewis structure, you're going to calculate the steric number. Once you know the steric number, you can determine the electron pair geometry. And then once you know the electron pair geometry, you can say, do I have some invisible spots? And if you do, then you can determine the molecular geometry. And once you know the molecular geometry, you can determine the polarity. So all of these topics build on each other. It is inherently cumulative, and you're going to have some questions about structure and polarity on your upcoming exam. And then hybridization, which we'll talk about today. Hybridization is also built off of all these things that you're talking about. And it starts with a Lewis structure. So it's good to know how to build a proper Lewis structure. The one last feedback I'll give you is I'm still seeing a lot of errors with respect to formal charge. So when you're making a Lewis structure and you're prioritizing Lewis structures, you really want to deal with formal charge and minimizing formal charge, and that will make your most stable Lewis structure. So if you don't know what I'm talking about when I say formal charge, go look it up. If you know what I'm talking about, but you're not sure you're doing it right, go look it up. That's the most common place that I'm seeing a lot of mistakes. Okay, I'm going to stop sharing this. I will put that in your preparing for the assessment. So thank you for that suggestion. Oh, I want to start sharing. I'm going to give Gerardo a platform. He has an issue of interest that I had shared with you earlier, but I want to let him give him the space to make his pitch. So Gerardo, you're on.
Thank you. Can you hear me?
I can.
So, hello everybody. As she said, my name is Gerardo. I'm one of your chemistry peers, but a lot of people on campus know me as Panda. So, one of the positions I have with ASTVC, which is our student government on campus, is Officer of Environmental Affairs. And ASTVC, for anyone new or unfamiliar, is student government. Um, but today I'm actually here to not talk about a environmental sustainability issue, but rather a health sustainability issue. Since DVC doesn't have a health center on campus, ASDVC is currently active in trying to meet the health needs of the students. So we're trying to build a health ad hoc committee like we did last year. So far, we've actually been successful in securing $100,000 in our funding to push that effort forward. But we still have a lot of work to do, and we're actually hoping that one day we can get all of our sister colleges to have adequate health centers so we can all be taken care of. Um, we are looking for new members and a chair this semester, so this would be a great leadership opportunity. And the cool thing about ad hocs is that they don't require participants to be a part of ASTVC. So if you've never heard of us before, you still can apply and you could still have the same power to vote on issues, the same capacity to actually be the chair, or just to be a part of the whole process of trying to get a health center or at least more health services, comprehensive health services on campus. So I did make a Google form, and then I'm also just going to put a link in the chat at the end of this, but you can also use the QR code that's on the flyer that I made. So thank you, Professor B, for putting that up. We are meeting tomorrow from Thursday, 1 p.m. to 2 p.m. And if you do have any questions, I have a lot of different guidelines, like what the chair or the other executive position responsibilities are, what the scope of work is, what does it mean to just be a participant versus just being a committee member with voting rights. So hopefully I've done my best to try to fill out all the questions in advance for you. So before I continue, does anyone have any questions? All right, cool. Well, hearing none, I'm going to go ahead and just post that information in the link again. And if not, you can always just like screenshot what's on the screen right now. And that's it. Thank you very much for your time, and I hope everybody does well with our assessment coming up.
I have a question.
Oh, cool. Yeah.
What exactly does the club do, or the program?
The program? Well,
Yeah.
essentially, ASDVC has a bunch of different initiatives and committees. So, for example, we have like a PR committee, we have a diversity committee. So we're basically just trying to fight for the rights and of students, and we're basically your voice. And one of the cool things that ASDVC has access to is every semester you have like a couple of registration fees and stuff. One of them is the student fee. So every semester you're probably wondering why there's a $5 or $10 fee assessed to like your classes. That actually goes into a pot which student government has access to, and through that we've done things like install refillable water stations on campus. We're actually currently trying to see if we can get more bike racks to encourage alternative transportation. So we're basically just trying to fill in what little inadequacies that administration hasn't done so. And I don't mean that in a negative aspect. It's just sometimes administration has their perspective in terms of what has a priority versus students, what they feel like is a priority. So we just want to make sure that if there is something that we could be doing to make campus life and student life better, then we try to. So in this case, because we don't have a health center, and actually out of 114 community colleges in California, I think we're one of only 4 or 5 that don't have it, which is really sad considering we're like top tier transfer school. So we just want to make sure we do have that service. So we're doing things like reaching out to other organizations. Right now we're actually communicating with Napa's college's health center to get inspiration and advice. And we're even considering doing like a remote health center in the meantime, something called like Timely MD, if you're not familiar. So it's just like we're trying to investigate to see if maybe for now we can just have like health providers remotely try to help students. So we're just trying to do anything and everything to try to make students' lives better. But in this case, for the committee that's happening tomorrow, it's for health and for both mental and physical health services. But if you're interested in something else, I would highly encourage you to come to a regular general ASDVC meeting, which is on every Tuesday from 2 to 4. So,
Okay, thank you. That sounds pretty cool.
oh, thanks. Well, you're pretty cool for being interested.
I'm going to, thank you so much, Gerardo. I'm saying it incorrectly. Gerardo?
Oh, nice rolling R's. Thank you. Muchas gracias.
De nada. I try. I tried to do the name coach assignment at the beginning of the semester, and like 2 people filled it out by the end of week 2, and I should have pushed. Anyhow, thank you for correcting me, and I'll try to do better in the future.
You can call me Chimichanga and you're fine.
I will not. Okay, I'm going to reclaim the mic, and I'm going to put a link in the chat to another whiteboard because we're doing a lot of drawing today, and I want to see how you're manipulating these topics before we come back together and answer them collectively. So I would appreciate it if you could click on the whiteboard link and sign in with a name that'll help me call on you. I promise to try to do better at facilitating it this week. I practiced a little more in the interim, and so hopefully my Wi-Fi is going to hold out and it won't be as buggy as it was last week. So click on the link in the chat to open up a whiteboard, and that's how we're going to do some drawing and sharing of drawings today. Okay, but mostly we're going to be in our lecture notes. So, molecular polarity is a topic that I largely did asynchronously, and I primed this topic by giving you a set of molecules, and some of them are smelly and some of them are not. And it turns out the reason why some are smelly and some are not is because some molecules are attracted to positively charged parts of your receptors in your nose. And when those molecules, those polar molecules, reach those receptors in your nose, they can bind to that receptor and trigger that neuronal response of smell. And so in order to know whether a molecule is polar, you first need a Lewis structure. Then you need to know the molecular geometry at those atoms. Then you need to know bond polarity. If you were watching the asynchronous videos, you saw me calculating differences in electronegativity value. The little delta sign means difference, and then EN stands for electronegativity. On assessment 2, you'll be given a table of electronegativity, or a periodic table that has electronegativity values. You're not going to be given this one. I'm going to give you one that just goes to 1 decimal place because it's a little easier to do the math on, and students get a little less confused with it. So look for that in the potentially useful information. You will get an electronegativity periodic table. All of these atoms have an electronegativity value except for noble gases. If anybody's caught up in your lectures so far, can someone tell me why the noble gases don't have electronegativity values? Any guesses? Let me step back and define electronegativity. Electronegativity is the property of an atom when it's in a bond to attract electron density towards itself. So it's a scale that tells you how likely is an atom to attract shared electron density towards itself. The bigger the number, the greedier it is, the more it wants to, and the more attractive it is to electron density. So having said that, why are the noble gases empty? Why don't they have an electronegativity value?
I'll give it a shot.
Yeah.
Is it because they've already got 8 valence electrons and they don't want anything to change because they're already perfect?
They don't largely participate in bonds. That's right. They have a full valence shell. They are satisfied in that way. Now, in your molecular geometry lab, you did have a couple of compounds that had xenon as the central atom. Those are known, but they are not common. So the reason that there are no electronegativity values for these elements is that they don't form compounds for the most part. The most electronegative element is fluorine. So electronegativity increases as we go across the periodic table. It also increases as we go bottom to top. I encourage you to watch the lecture video and learn how to explain why these periodic trends are the way that they are.
Professor, I have a question.
Yeah.
Could you go back to the chart? So just like, because you just reminded me of a question I was trying to answer for myself, because we did have that xenon molecule, but I was wondering, why does it reacting with something if it's xenon? So like in fission, I guess when you're just shooting neutrons to something, can you force like a noble element to have like like just a few seconds of like an existence as a molecule before it goes back to being a noble or something? Like, is that why that is? Or
The reason xenon can form compounds is because it is such a large element and those valence electrons are fairly distant from the nucleus. And so they're more available to exchange with other elements. But it's not a very stable compound, and those bonds are transient, and you keep them in a real cold temperature and they will, they're highly reactive. Basically, those xenon compounds are a really good source of F+, which is a very uncommon species because fluorine is very electronegative. Fluorine would much prefer to be F-. And so anyhow, long story short, the compound xenon tetrafluoride exists, but the reason you don't have measurable electronegativity values is because they're not very common, those compounds. And then to answer your second question, most of the new elements that we know of happen because we bombard things at high energy and high speed in a particle accelerator. I'm not sure if that's what you were asking about, but further,
yeah, that was pretty much.
further than that, I feel like it's going to derail my rhythm. So I want to get back on my rhythm.
That's it. Now you answered my question perfectly. Thank you.
Okay, cool. So the first compound I want to talk about with respect to smell is ammonia. If some of you have ever had smelling salts put up to your nose, you know it's a very unpleasant aroma that hits your nose. If you've ever done some cleaning with ammonia-based cleaners, you know that it's a very pungent aroma that hits your nose. So in ammonia, we have nitrogen and hydrogen bonds. So nitrogen has an electronegativity of 3.04. Hydrogen has an electronegativity of 2.1. So nitrogen, with its higher value, is more electronegative, more attractive to electron density. If we want to take the difference in electronegativity, we subtract the smaller one from the bigger one. So we get a value of 0.94. On our scale of polarity, 0.94 as a difference in electronegativity puts us solidly in that polar covalent range. So nitrogen-hydrogen bonds are polarized. I'm going to come back down here and I'm going to draw the structure in 3 dimensions. Most of you correctly assigned the geometry of this molecule as trigonal pyramidal. That is the molecular geometry that you see for that nitrogen. And what we just learned was that those bonds between hydrogen and nitrogen are polarized. Since hydrogen is less electronegative and nitrogen is more electronegative, we can think about little vectors on each of these bonds pointing towards that nitrogen. So the vectors show you the direction of electron flow. They want to hang out with nitrogen. They want to leave hydrogen in that shared bond. And the back of that symbol has like a little plus sign telling you that the other atom is losing that electron density and becoming partially charged. So since nitrogen is going to get more electron density than it normally has, it takes a partial negative charge. And each of these hydrogens are partially positively charged. So when ammonia gets smelled up your nose, what atom in ammonia is most attracted to your smell receptor? Nitrogen or hydrogen?
Nitrogen?
That's right. The smell receptor is positively charged. Remember, opposites attract. So we're going to align that ammonia so that the nitrogen has that attraction between itself and the smell receptor. So this is called a dipole interaction. And we'll talk about them when we talk about intermolecular forces in our next chapter on energy. So basically, this polar molecule is attracted to your smell receptor based on opposite partial charges. These are called partial charges because those atoms are still bound to each other. The electron does not get transferred. It is still shared between the two elements, but it spends more of its time, it's more probable to find that electron density around the nitrogen than it is to find it around the hydrogen. I will tell you that carbon-hydrogen bonds are nonpolar. Carbon-fluorine bonds are polar. Many of you, correctly had the structure as a tetrahedral. Ooh, I don't want to do a 90-degree angle. I'm just like up against the sheet of paper over here. There we go. It all starts with a good drawing. I want you to redraw difluoromethane in the smell receptor as you think it would exist. So if you know that carbon-fluorine bonds are polar, you know that fluorine is the most electronegative element in that molecule. What part of that molecule is most attracted to your smell receptor? I want you to draw it on your whiteboard. I'm going to take a look at your whiteboards. So put a little plus sign at the bottom of your whiteboard and then orient your drawings towards the smell receptor, that positive smell receptor. I don't see anybody in my whiteboard room. Now I do, now I see you. So put that little positive sign, and then how would you draw your molecule oriented towards that positive sign?
Which molecule are we doing?
You're doing difluoromethane. I want to know, how would we orient that molecule towards that positive smell receptor? I did turn it on turtle mode so that those of you who are having connectivity, if you have a drawing that you're happy with, I want you to click save at the top of your whiteboard so that I can see what you're drawing, because it's not automatically saving what you're drawing. So you have to tell it to save. I love it. Good. I'm seeing some pictures. Great job, those of you who have saved. You have oriented the molecule correctly. I want to give other folks a minute to get their drawings locked in. All right, I'm mostly seeing what I would expect to see, which is people are assigning that there's a partial negative charge on those fluorines, and they recognize that the smell receptor itself has a positive charge. And so some of you are orienting the molecule such that that fluorine is directly towards that positive receptor, and some of you are putting it so that both of the fluorines touch. I think both of those pictures are appropriate to draw because they both illustrate that there are partially negatively charged atoms that are attracted to that receptor. I'm going to go back. Okay. So drawing that molecule oriented such that fluorines, whether you have both fluorines and they're both attracted to that smell receptor, or whether you primarily had one or the other, I think there's not enough information here to go on in terms of saying exactly how it's oriented, but the fact that those partially negative atoms are attracted to the positive receptor is what we want to see. The last molecule we have is formaldehyde, so I'll put that one up. Intuitively, hopefully now you know carbon-hydrogen is a non-polar bond. That's not a polarized bond. What about carbon and oxygen? It is a polarized bond. Based on periodic trends, which one do you think is more electronegative, oxygen or carbon?
Oxygen.
You got it. Oxygen's closer to fluorine on the periodic table. So that oxygen is going to have a partial negative. That carbon is going to have a partial positive. So formaldehyde, also a smelly compound, is going to line up and orient to put that partially negative oxygen near that smell receptor. If I were to ask you a question, which substance would have the strongest smell, what do you think the first thing you would want to do with all these formulas is? Draw yourself a Lewis structure. Think about the molecular structure of all of these. So I'm going to give you some options for what you might see. So C2, actually, I want you to just get me some Lewis structures for C2H6O. I'll give you the other ones. I want you to come up with a particular structure. So erase your whiteboard, put a new compound on it that has the formula C2H6O. I want to give you some practice with Lewis structures. When you have something you're happy with, I want you to save it. I want to see what you got. When you have a Lewis structure that you think you are on board with, I want you to save your board and show me what you got. Yeah, I like it. Relina has one structure and Kino has the other one. I'm going to put their structures up on my whiteboard so that you all see what I'm seeing. So this is one of their structures and the other one I see. Is this one. What's the relationship between these two?
I don't see anything.
Oh, I'm going to push it to everybody. I can also start sharing again.
I see it now. Thank you.
What's the relationship between these two structures? Anybody know the vocabulary word? It starts with an I.
Isomers?
Isomers.
Isomers. These are isomers. These are isomers. Do you think they have any polar bonds?
Yeah.
They do. They do have polar bonds. We were just saying that carbon and oxygen is a polarized bond. So there are little dipole moments where that oxygen is greedy. So these are polarized bonds. Hydrogen and oxygen is also a polarized bond. So that oxygen is partially, oh, not partially positive, partially negative. And partially negative. Why did I get all thick like this? I want to change my.
Click on the little like X next to the thing. It'll change the line width. Like click on the pencil and then right below the pencil there's like that like X.
I just want to do. I promised I.
It's the little X next to the gear on the bottom. Like.
I know I'm clicking on it.
Oh, sorry. It looks like you're clicking on the other thing.
It's not letting me do it. I'm going to clear everything and see if that. No, I don't want to do it. All right, I'm going to go back. All of a sudden now I only have, oh, there we go. Okay. Hopefully this works. Oh, I need a color again. There we go. Okay, I'm just gonna be a little bigger. It's fine, it's all good. I'll fix it in a minute. So we have isomers. Nope, we're definitely gonna take care of that. Okay. Promise not to be a rookie mistake. And then here it comes. Okay. Well, I don't like that one either, but we're gonna go with what we got. So we have partially negative compounds. Do we have polar molecules? You don't really know because we haven't drawn the structures in the shape that they exist in. So we need to assign a geometry to each of these atoms. So carbon, how many atoms are attached? 4. How many lone pairs? None. So I have a steric number of 4. I have no lone pairs. What's the geometry at that carbon?
Tetrahedral?
You got it, tetrahedral. How about at oxygen? What's the geometry at oxygen? Both of those carbons are tetrahedral. What's the geometry of that middle oxygen atom?
Bent?
Bent, you got it. How'd you get there, whoever said it?
Well, I knew we had 2 lone pairs and 2 atoms attached, so I just knew it was bent.
So the steric number, 2 atoms attached and 2 lone pairs gives me tetrahedral, but 2 of those spots are invisible, so I have a bent structure. Some of you are struggling with how to draw a Lewis structure when multiple atoms are connected together in a single molecule. Let me show you how I'd go about it. I'm going to take that oxygen atom, which is a central atom, and I'm going to make it look bent by putting both of those connections to the carbons on bonds that are in the plane of the paper. Well, now each of these carbons is tetrahedral, so I'm going to draw my other bond that's in the plane of the paper to hydrogen. And then I'm going to draw some wedges and some dashes on the other hemisphere of each of those carbon atoms. So that's just a process by which I can draw this structure with multiple atoms attached, showing the shapes at each of those atoms. Okay, how about the other isomer? I want you to practice drawing the other isomer. Assign the shapes at each of those atoms, and then try to draw that structure in as a perspective sketch. My practice is to start by drawing something that's in the plane of the paper first. So that oxygen is still going to be bent. I'm going to make the connection to carbon in the plane of the paper so that I can draw the connection to the other carbon in the plane of the paper. Now I have my whole skeleton in the plane of the paper, and I can decorate with dashes and wedges. There are tons of other ways to draw this, but the long and short of it is this is one systematic way to draw it so that you show all the shapes that you want. In both of these, we see that there's still dimensionality. Those polar bonds are still pointing towards that more electronegative atom. There's nothing unbalancing that distribution. So yes, these are polar molecules. They have a partially negative oxygen. Let's go back and look at the other molecules that were in your problem. I gave you some Lewis structures. So we know this one is polar because we just looked at that on the previous page. How about acetylene, C2H2? Are any bonds in that polar?
No.
Bond between a carbon and itself, the difference in electronegativity is going to be 0. Bond between carbon and hydrogen, not polarized. We already know the smell receptor has that little positive charge, so I don't think acetylene is that smelly. Magnesium chloride. This is an ionic compound. Do you think it gets in the gas phase very easily? It's a salt, an ionic solid. It does have ions that are polar, but the fact that it is an ionic solid means it's not volatile. It can't really get to your nose. So I don't think we're going to smell that much magnesium chloride either. Methane is made entirely from nonpolar bonds. Here's the tricky one for most students. They don't understand why carbon tetrafluoride would not be smelly. All of these bonds are polarized. All of these carbon fluorine bonds are polarized. If I think of each of these little bonds to fluorines as vectors and I pull on all of them, equal and opposite, this shape can't go anywhere. If I pull on all of these bonds equally and oppositely, then all of those vectors cancel. So all of the vectors add up to 0 dipole moment for the molecule. So just because you have polar bonds does not mean you are a polar molecule. You only have a polar molecule when you add up all the vectors of the bonds, and when added up, the molecule has a dipole moment. So for instance, I'm going to just draw a dimethyl ether that we just had on the previous page. I'm not going to worry about the tetrahedral angles. I'm just going to focus on the polarity. Each of these bonds are polar. When I add up those bonds, I get a molecule dipole moment towards that oxygen and away from the carbons. So this is the molecule dipole moment. And it is the sum of the bond dipoles. So just because you have polar bonds in the molecule doesn't make you a polar molecule. You must add up the polar vectors in a molecule. And if they add up to something, then yes, you have a polar species. But if they add up to nothing, we have no dipole moment for CF4, even though we have very polar bonds. Okay. Hopefully that was a little bit of a review from an asynchronous lecture. This table I found is incredibly useful since they updated the book. It's now table 11.2, but it's the very same table that really walks you through how you can determine whether or not a molecule is polar. Before you do anything, calculate. I can spell calculate. Calculate the delta En for bonds in the molecule. In order to have a polar molecule, you must have polar bonds. To have a polar molecule. Now, when you're taking that difference in electronegativity, you can be as low as 0.5 or as high as 1.9. This difference tells you that you have polar covalent bonds. So when you take that electronegativity difference, a difference of 0.5 to 1.9 is going to tell you that you have polar covalent bonds. And then once you have polar bonds, you want to think about how do you add up those vectors in three-dimensional space. If all the bonds are equally polarized and you are in trigonal planar, then they will each pull equal and opposite away from each other. You will be nonpolar. If you have a linear species and both of the bonds are polar but pulling in opposite directions, again, you have a nonpolar species because the vectors cancel. If you have a tetrahedron, all of those pulling in equal and opposite directions, then you are nonpolar. Let me just put up an alternative. What if I have this molecule? There are 3 fluorines and 1 chlorine. Do you think I have a polar or a nonpolar molecule? Well, I know that carbon-fluorine bonds are polar, so I'm going to draw those little dipole moments for those bonds. I know all of those bonds are polarized. I'm going to go check on carbon and chlorine. I'm going to go back to my electronegativity chart. 3.16 minus 2.55. So 3.16 minus 2.55, that's greater than 0.5, so I have a polar bond. But look, the difference between carbon and fluorine is much greater than the difference between carbon and chlorine. So even though I have a polar bond, it is not as polar as the carbon fluorines. And so my vector is going to be a little bit shorter. So all these fluorines are pulling in one direction. The chlorine is pulling a little bit back, but mostly the electron density is moving towards those fluorines. So the overall molecule dipole moment is not 0. There is significant movement towards those fluorine atoms. So these are my partially negative atoms. And carbon would have a partial positive charge. So that is an example of a tetrahedron where there are polar bonds, but they don't all cancel because they have a different amount of polarization. So the first things first, you got to determine the shape. The second thing, you got to think about, do those vectors add up to something or do they add up to nothing? So you sum the vectors to get a molecule dipole. If you add up all those vectors and you get 0, then you're nonpolar. If you add them up and you don't get 0, they don't all cancel, then you're polar molecule. And then the last thing that I emphasize is think about the strength of the dipole. Think about the strength of the dipole. Okay, that's about all I wanted to say about polarity. I haven't checked the chat at all. Can somebody be my chat checker and let me know if there's anything hanging out in there? Or unmute yourself and feel free to ask. Hopefully you now have a little bit of an understanding about polarity. You can go review the asynchronous lecture and attempt the last part of your lecture notes. I want to move into the last key topic before our assessment, which is called valence bond theory. I want to emphasize I am teaching this differently. Listen to me. When I ask you questions on your assessment, I'm going to encourage you, my rubric is built off of the assumptions that I'm teaching you. I know they subtly disagree with what the way the book is teaching you. I'm an organic chemist. So I'm going to teach you the way that's going to help you if you intend to go on to 226 and 227. The person who wrote your textbook is an inorganic chemist, highly theoretical chemist. He's making different assumptions than I am. So pay attention today. Hopefully you get a grasp, and hopefully you get a little more practice with the hybridization assignment. So valence bond theory has 3 tenets. And it relates to how molecules are constructed. So we spent a lot of time in week 6 talking about atomic orbitals, s, p, d, and f orbitals. Those are the orbitals that live on an atom, and they can be used to connect to other atoms. The way that we build bonds is by overlapping orbitals from each atom to form the bond in different ways. And the way that those orbitals overlap determines the type of bond that you're forming. Those are the 3 tenets of valence bond theory. Now, let's try to, just at the outset, use valence bond theory to understand methane. Just from where we are right now, what we know about methane, the perspective drawing of methane, I've drawn it once today, I'll draw it again. We call this shape a tetrahedral shape. Do you think this structure has the same or different bond lengths? Why do you feel that way? Somebody who has an assumption, what do you think? Are all those carbon-hydrogen bonds, are they the same length or are they different? Don't all jump at once.
Nancy said same on the chat.
Okay, but why? Why, Nancy?
Christopher says it's the same charge, same length.
Same charge, same types of atoms. This shape has a lot of symmetry in it. I'll put the shape back together again. Oh, here it is. So we have this tetrahedral shape. All the angles are what? 109.5. All those atoms are the same to each of those bonds. They're all hydrogen atoms. So yeah, I think you're right. They're the same bond lengths. We have the same types of atoms. We have the shape that is fully symmetrical. So I feel like they should be the same. I want you to draw me the valence electrons for hydrogen. What's the energy level diagram for the valence electrons in a hydrogen atom? Where are they? What's the ground state electron configuration for hydrogen? I don't see the chat, so I'm going to need somebody to watch the chat and read it out if you see somebody put something in there. My screen is not big enough to see all the things. Come on, folks. Where does the valence electron in a hydrogen atom live?
1s1.
You got it, 1s. I got 1 electron in a 1s orbital. What about carbon?
1s, 2s, and 2p.
1s2, 2s2, 2p. How many electrons are in 2p orbitals?
2.
2. Okay, what's the shape of a 1s orbital? If I were to describe the shape. What does a 1s orbital look like?
Is it a teardrop?
That's a p orbital. looks like an infinity symbol. An s orbital just looks like a sphere. So a 2s orbital has a node, but still from the outside looks like a sphere. A 2p orbital looks kind of like that infinity symbol. Sorry, I didn't draw these on different axes. I have an X, a Y, and a Z. 2p orbitals. So when I think about overlapping these atomic orbitals, does this shape make sense? All these p orbitals, I'm actually going to start drawing them in a different shape. I'm going to put carbon at the center. Those valence electrons for carbon, they are in a 1s orbital. So I'm going to draw that like a yellow, or sorry, a 2s orbital. So I have a 2s orbital, but it's full. Can any more electrons go in that orbital? No, it's all full. What about the 2p? Well, I have 2p orbitals. Each of them has 1 electron in it. So basically, if I were to use what I know about the atomic structure of carbon, what would be the formula for methane? CH2. It seems like it only wants to overlap with 2 different hydrogen atoms because those hydrogen atoms each have 1 electron to buddy up with that carbon electron. Is that what we observe? No. The shape that we see for methane is tetrahedral. We have 109.5 degrees. If we were to use the atomic orbitals that we know about for carbon, the angle here is 90 degrees. That's not what we observe. The formula here is CH4. If we were to use what we know about the atomic orbitals that need a friend, we would predict CH2 as the formula for methane. So the atomic orbitals that we know about are not enough to explain what we observe when we look at methane in a bonding way. So we need a different model. And that model is called hybridization. What do you think of when you think of the word hybrid? Probably think of a Prius. What does the word hybrid even mean? It's a mixture of 2 or more things. So when we talk about chemistry using the word hybrid, it's not a whole lot different than hybrid in the world, in the English language that you've used. So hybrid, something that's a hybrid is a mixture of 2 or more orbitals. So in this case, we're going to be mixing orbitals. Hybridization of atomic orbitals. A hybrid orbital is something that's formed from mixing 2 or more orbitals. Okay. I want to ground this conversation in a topic that we already know about, which is steric number. Since the whole purpose of needing this new model called hybridization is to explain what we see, the geometry that we see, then let's ground ourselves in how we got to that geometry in the first place, which was the steric number. So here's my structure for methane. I'm going to redraw it up here. What's the steric number for carbon? I have 4 atoms attached. I have none lone pairs, which means I have a steric number of 4. That steric number means I have 4 electron groups around that carbon atom. Is everybody following me so far? I calculate that steric number. That steric number tells me that around that carbon, there are 4 different groups of electrons that need to occupy space as far apart as possible. That's how I get that tetrahedral geometry. Well, if I have 4 electron groups, then I also need 4 hybrid orbitals. The bonds that we observe in that structure are going to be constructed with hybrid orbitals. These are called sigma bonds. I'm going to use that Greek symbol sigma, which looks like a kind of like a 6, but like a flattened 6. And when I went back over it, it looks kind of sad. So let me put this again. These are sigma bonds. Furthermore, these are sigma bonds between carbon and hydrogen. So we're overlapping orbitals on a carbon atom with a hydrogen atom. Now, where are the valence electrons for carbon? The valence electrons for carbon are the ones that are available to do the bonding. So those are the electrons that are in the 2, shell 2. You have 2s and 2p2. So 2s2 and 2p2. Now, how many total orbitals are in the picture that I just drew? Not that have electrons in them, but total. How many orbitals are in that valence shell for carbon?
4.
Great, 3 plus 1 is 4. If I need 4 hybrid orbitals, I've got to mix all those atomic orbitals to make my new hybrid orbitals. So in this process known as hybridization, those 4 orbitals, I like you to think about it like a blender. I want to feel festive today. So here's my blender, okay? I'm going to throw in 3p orbitals. I'm going to throw in 1s orbital. And instead of, now I recognize that I'm probably going to get you really confused. So let me be clearer. 3 times 2p. So I'm going to throw in all of those 2p orbitals. 1 times 2s. So I'm going to throw in that 2s orbital. And out of the blender comes 4 new degenerate hybrid orbitals known as sp3 orbitals. So I throw in that blender, I throw it in the blender, I mix it up, and then I spit out 4 orbitals that are equal in energy. Do you notice that they are higher in energy than the s? But they are lower in energy than the 2p. They literally are a hybrid. They are closer in energy to the p orbitals because there are 3 p orbitals in that blender. So they have more p character. They have a larger percentage of p. How many valence electrons are in the carbon? 4. Well, I'm going to put them in my hybrid orbitals just like I would have normally, which is to fill them singly before I start pairing. Now, in this hybridization picture, how many bonds does it look like carbon wants to form? Hopefully you see that there are 4 lone electrons screaming that they want a friend. So this hybrid model explains why carbon prefers to form those 4 bonds, 4 sigma bonds. So the hybrid orbitals are used to form sigma bonds. So if I were to be really complete in labeling how these sigma bonds are, I'm overlapping the s orbital of hydrogen with a new sp3 orbital from carbon. Again, I think students get really confused about that term sp3. It literally means 1 s orbital plus 3p orbitals. Not 3p as in level 3, but 3 quantity 3. So that symbol tells you that overall 4 orbitals mixed. Well, if you throw 4 orbitals into the blender, then 4 orbitals have to come out of the blender. An sp3 orbital, I'm not going to test you on this. I'm not going to ask you to draw the shape. You'll see better pictures in your book. So let me show you the picture in your book. I had it pulled up, and then wouldn't you know, Pearson logs me out. It's all good, Pearson.
I have a quick question while
Yeah.
you're waiting. So when I was doing the homework, I had a little trouble figuring out between SP3 and SP2, and I think you just answered the question, but that just basically tells you how many orbitals in the p level have an electron in it, correct?
No, it tells you how many orbitals mix to make a hybrid. So sp2 would tell you that one s orbital mixes with two p orbitals, and we're going to get there in a minute.
Okay.
Okay, here's what an sp3 orbital looks like. If you took that one s orbital and you threw it in a blender with these three p orbitals, you get kind of like a p orbital that's fat on one side. Is kind of what it looks like. This is the node of it, or sorry, not the node, the lobe of it that forms the bond. This is the bonding part of the orbital. The tiny part on the back is the anti-bonding part of the orbital. We'll talk about bonding and anti-bonding when we get to molecular orbital diagrams, which will be on your next exam. So stay tuned with that. This is the shape of the hybrid orbital. And if we orient those in three-dimensional space, you see the tetrahedron. Now, in the picture I'm about to draw in your notes, we don't draw the backside. We don't draw the anti-bonding lobe of it. We just draw these fat overlapping lobes that are used to overlap and form the bond. So let me show you what I'm talking about. I do want you to be able to draw a picture of bonding in this structure. So let me put that picture in your notes. The picture should start with your central atom. Now this atom is formed with three sp3 orbitals, and that was not the same shape. I want to be as clear as possible. I do not want you to draw me dashes and wedges when I ask you to draw hybrid orbitals overlapping to form different molecules. I want you to draw the lobe, and then I want you to label what type of orbital this is. So all of these are sp3s. I have 4 equivalent sp3 orbitals. They are overlapping with the s orbital of hydrogen. What's the shape of an s orbital? It's just a circle. So I'm going to put the circles to overlap with those sp3 orbitals. These are all hydrogens. These are all hydrogens. And they are all s orbitals. So I'm taking the bubble of the s orbital and I'm overlapping it with the p orbital. So what I see in this molecule are 4 sigma bonds between carbon and hydrogen, and they are formed by overlapping an s orbital with an sp3 orbital. How are we doing? Sigma bond is a bond formed on the axis of bonding by overlapping atomic or hybrid orbitals. So sigma bonds are formed by the overlap of atomic orbitals like this s orbital from hydrogen, and or hybrid orbitals, which are formed by mixing atomic orbitals to form new types of atomic orbitals, these hybrid atomic orbitals. Sigma bonds are on the axis of bonding. This is kind of important because Sigma bonds have a unique property. They can freely rotate. So I'm going to build a molecule. I'm building ethane right now, so C2H6, and you can see in my model, I can freely rotate about that bond. The orbitals are overlapping on the axis of bonding, and that bond has free rotation. So if all I have are just sigma bonds, then I can freely rotate. Sigma bonds that are only sigma bonds can freely rotate. How are we holding up?
Emily just had a question in the chat. She just wanted to know if we need to know what angles are associated with what shape for the test.
You need to know the basic shape angles. So trigonal planar is 120, tetrahedral is 109.5, trigonal bipyramidal has 90 degrees and 120 degrees. Octahedral is all 90 degrees. So you need to know those basic angles. You also need to be able to use arguments around electron repulsion to explain why an observed angle might be different than the ideal angle that was predicted by that shape.
Cool, thank you.
All right. As with everything in the online environment, things take a little bit longer than I intended. So I'm going to keep going and not make this a breakout. I was going to have this be a breakout, but I'm just going to keep rolling. Methylamine is an organic compound. I don't know why I said with two different atoms. With two different central atoms is maybe what I meant to say. Let's draw the Lewis structure for methylamine. I'm going to go ahead and give it to you. I expect you to be able to produce Lewis structures on demand. Okay, I want you to determine the steric number for carbon and the steric number for nitrogen. So carbon, how many atoms are attached? I heard you all say 4. How many lone pairs?
0.
None. So I have a steric number of 4. How many hybrid orbitals do I need? 4. So what hybridization do I need? sp3. sp3 tells me that I mix all 4 of those orbitals and I get 4 new hybrid orbitals. Let's do that same process for nitrogen. How many atoms attached?
3.
3. How many lone pairs? 1.
1.
So I also get a steric number of 4. That means nitrogen also needs to be sp3 hybridized. I want you to practice. Draw me the energy level diagram for nitrogen that's not hybridized, and then draw me what you think the sp3 orbitals look like on an sp3 hybridized nitrogen. So where are the valence electrons? How many of them are there? Hopefully you all realize that nitrogen is also in period 2. It has 5 valence electrons. I'm going to mix that nitrogen up to get myself 4 new hybrid orbitals. These are sp3 orbitals. How many valence electrons do I have? I have 5. So I'm going to put them in these orbitals. 1, 2, 3, 4, 5. And what you see is that we have 1 lone pair in a hybrid orbital. So whenever an atom, a central atom has lone pairs, that lone pair is an electron group. It lives in a hybrid orbital. We put it in a hybrid orbital. I have 3 hybrid orbitals that are screaming that they want to bond. So nitrogen forms 3 sigma bonds. The hybrid orbitals are used to form sigma bonds. So this hybridization tells me that nitrogen wants to form those 3 sigma bonds with those sp3 orbitals. So let's try to draw a picture. I'm not going to draw it right away. I want you to practice drawing what would it look like for carbon and hydrogen, carbon, what would this species look like if I were to draw all the orbitals that overlap to form it? I'm going to start with carbon. What hybridization is carbon?
SP3.
sp3. That means I have 4 equal lobes on that carbon that are all sp3 orbitals. I'm going to draw all those sp3 orbitals. How are we doing? Now, what else is carbon bonded to? It might help you to revisit your picture. Carbon is bonded to 3 different hydrogen atoms. Well, what orbital do those hydrogen atoms have? They only have a 1s orbital. So they can't hybridize. They have no other orbital in their valence shell. They can only offer their s orbital to overlap. So all these hydrogen s orbitals overlap with the sp3 orbitals. What I see right here is that I have 3 sigma bonds between carbon and hydrogen. The carbon is sp3 hybridized. The hydrogen has an s orbital. Whenever I ask you to list the bond types in a molecule, this is the type of list that I want you to produce. The type of bond that it is, sigma or pi, we're going to talk about pi bonding in a minute. How many of them are there? What atoms overlap to form that bond? And what types of orbitals overlap to form that bond? So this is what I mean when I say list the bond types in a molecule. Well, there's a 4th bond. Carbon wants to form a 4th bond. Who is that 4th bond to? It is to a nitrogen atom. Well, sigma bonds are formed by hybrid orbitals. What's the hybridization of nitrogen? Also sp3. So I'm going to draw a lobe that overlaps with the carbon sp3 lobe, and it's going to be a nitrogen sp3 orbital. So I have 1 sigma bond between carbon and nitrogen, both of whom are sp3. Well, nitrogen is sp3 hybridized, so it has 3 more sp3 orbitals. Because sp3 means I get 4 hybrid orbitals, 4 sp3 hybrid orbitals. 2 of those are overlapping with some hydrogens to form nitrogen-hydrogen bonds. So again, I'm going to draw 2 circles. Those are my hydrogen s orbitals. And then what is in the last sp3 orbital? That is simply my lone pair. That's a non-bonding lone pair of electrons. In fact, let me give it a different color so it's a little more visible. That's just my non-bonding lone pair. Each of these, yeah.
For the bonding types, when you write the bond between the sp3 of the carbon and the nitrogen, does it make a difference if you write the nitrogen first and then the carbon? The way you wrote it on, okay.
No, it doesn't. I typically will write less electronegative, no, I'm not even going to say that. It does not matter. It matters not one bit. Okay, but my list is incomplete. What bonds have I not put on here? I have 2 sigma nitrogen hydrogens between an sp3 nitrogen and the s orbital of hydrogen. And then I have 1 lone pair which is in a nitrogen sp3 orbital. So these are all the bond types. And if I were to ask you about the lone pair, lone pairs live in hybrid orbitals. When I'm asking for bond types, I'm asking for a list of the types of bonds in the molecule. Now, total, I have 3 plus 1 is 4, plus 2 is 6. Do I have a total of 6 bonds in this molecule? 1, 2, 3, 4, 5, 6. That's like a nice way to check my work. Did I list all the bonds correctly? And I did. I'm at the point in my semester when I need to do that type of check. How are we holding up? I put a lot,
but it's being explained very well.
Anybody have any questions about sp3 hybridization before we go on? So just a reminder, what we know about atomic orbitals is inadequate to explain the shape we see. So as chemists, we need a new model to explain why all these bond angles are different, why all the bond lengths are the same, why all these bond angles are the same, and why all the bond lengths are the same. And that strategy is a new theoretical construct called hybridization. So building hybrid orbitals from the available the available atomic orbitals so that you can build the molecules that you see. How do you know how many hybrid orbitals you build? Well, you ask yourself how many electron groups need to be satisfied. So you take that steric number that you were already calculating to determine the molecular geometry, and you use it to figure out how many hybrid orbitals you need to build that shape. The hybrid orbitals that you build are degenerate, meaning they are equal in energy. They are a mixture of S and P, so they are somewhere in energetically between those two. For an sp3 orbital, they are closer in energy to the P's than they are the S's, because that hybrid has a lot more P character in it than it has S character in it. Electron groups can be bonds or non-bonding electrons. Those hybrid orbitals can form bonds, but they can also hold non-bonding lone pairs. I want you to be able to draw the types of interactions that overlap to form the bonds in the molecule. I want you to be able to label the types of orbitals that are overlapping. I want you to be able to list all of the bond types, including any hybrid or atomic orbitals that overlap. These two processes are complementary, meaning you probably can't build this unless you can make this list. If you make this list, it'll likely help you build this. Those two things build on each other. Okay, let's talk about sp2 hybridization, since Kate brought it up a minute ago. The Lewis structure for ethene, C2H4. Looks like this. What's the steric number for carbon in ethene?
4.
No. I have 3 atoms attached and none lone pairs, so I only have a steric number of 3. Remember, it's not number of bonds to carbon, it's number of atoms attached. So this carbon is attached to 2 hydrogen atoms and 1 other carbon atom. So 3 plus 0 is 3. So how many hybrid orbitals do I need? I need 3 hybrid orbitals. Well, if I started carbon just like I did on the previous page with a neutral carbon atom configuration that looks like this, I don't need to mix all 4. I only need to mix 3. Well, when we're mixing 3, we mix the S with 2 other p orbitals. So into our blender is going to go the 2s orbital and 2 of the 2p orbitals. So if we throw 3 orbitals in the blender, we get 3 orbitals out. These are called sp2 orbitals. Now, what happens to that p orbital that didn't go in the blender? Nothing. It stays where it was. It keeps its electron. But any other orbitals that mixed hold the remaining valence electrons. So this p orbital that didn't get thrown in the blender, it's still hanging out over here, not in the blender. These 3 valence electrons go into the 3 hybrid orbitals. How are we holding up? So far, so good? These electrons that are in the hybrid orbitals want to make 3 sigma bonds. This p orbital still needs a friend. It's still alone. It needs a buddy, a partner to be full and complete. When p orbitals overlap, do you know what type of bond you form? You form a pi bond. The p orbitals that didn't get hybridized overlap to form a different type of bond. Let me show you what that looks like. Okay, here's my 2 carbon atoms. That's probably too far apart for this to be my clearest drawing ever. I'm going to stack the deck in my favor. Okay, let's put them a little bit closer together. These 2 carbons, does everybody see in the Lewis structure how these 2 carbons have 2 bonds between them? Everybody see that? There's a double bond here. Well, now you're going to get to learn a little bit more about what a double bond really is. One of those bonds is a sigma bond between the 2 carbon atoms. So one of the bonds in a double bond is the overlap of the hybrid orbitals, which are now sp2 orbitals. So there's a sigma bond between those 2 carbon atoms that forms from the overlap of those 2 hybrid orbitals. Again, carbon is now sp2 hybridized, so the little label inside says sp2 and not sp3. Everybody with me so far? Are there any other sigma bonds in this molecule? Yes. Every one of these carbon-hydrogen bonds is a sigma bond, formed by the overlap of the hybrid orbital with hydrogen's 1s orbital. So I'm going to draw the sp2 lobes on each carbon. And those are going to overlap with the hydrogen s orbitals. To form 4 new sigma carbon-hydrogen bonds. These are formed between the hybrid orbitals of carbon and the s orbitals of hydrogen. How are we doing? there's one remaining orbital that we need to deal with, and that's this p orbital. What does a p orbital look like? It looks kind of like an infinity symbol. It has two lobes. So here's my carbon p orbitals. Each of those p orbitals holds one unpaired electron. So what I want you to think about is these p orbitals that are sitting here perpendicular to the plane of the molecule, they realize they're only half full. They're incomplete. And they say, oh, hello, will you complete me? And they overlap by sort of bending towards each other. So I'm going to draw some overlap just by sort of connecting them. In your book, I'm going to stop sharing here. I'm going to start sharing here. In your book, they draw this interaction like, basically like a clamshell. They go ahead and they draw in that overlap between them, much like I'm doing. You see that there's a single electron in each of these p orbitals, and they are overlapping around the axis of bonding. So there's an axis of bonding, that's where my sigma bond is. And there's around the axis of bonding, and that's where my pi bond is, around the axis, not on the axis, around the axis.
Professor?
Yeah.
Is there any particular reason why they picked the word pi? Like, does it have anything to do with 3.14? Or...
I don't think so. I don't know the origin of the word sigma and pi, to be honest. I assume it was a German, but I don't know that to be true.
Well, that explains everything.
A lot of things in chemistry were brought to us by Germans in terms of the language that we use. But I don't know the origin of that particular one. So what we're drawing here is a pi bond. So we have one pi bond. And how is that pi bond formed? It's formed by the overlap of the p orbitals on each carbon atom. Pi bonds are formed by the overlap. Whoop, that's not how you spell overlap. Of p orbitals around, not on, around the axis of bonding. Okay, remember you see on my paper, we've got two p orbitals and they're going towards each other to overlap to form that pi bond. Everybody with me? Maybe not, maybe so. I want you to look at my hands. Here's my p orbitals. Think about them as being in the same orientation, 90 degrees from the axis of the molecule. Now I'm going to turn that molecule on its head. So now you're looking right down that double bond. So this hand is a carbon and this hand is a carbon. What happens if I rotate my carbon atom? Are these overlapping anymore? My daughter, y'all, my baby has learned to say hiya, which apparently is how my husband puts her clothes on. So now all I can think of is hiya. All right, so hiya, am I overlapping? I am not. I have broken that bonding interaction. I better line up again. In order for pi bonding to occur, these orbitals have to be aligned. If one of them rotates, then the lobes can't overlap anymore. That breaks the pi bond. Don't do that. So these p orbitals, in order to form that bonding interaction, have to overlap. They cannot rotate. And so double bonds don't have free rotation. I cannot, here's a molecule that has a double bond. I can't take my model and rotate it. It's impossible without breaking those plastic bonds. So there is no free rotation around pi bonds. If a bond is built with a pi bond, they must stay aligned. P orbitals must be aligned to form pi bonds. P orbitals must be aligned to form those pi bonds. How are we holding up? Total in my list of bond types, I have 4 + 2 is 6 bonds. I'm just going to do a quick check because I don't trust myself. How many bonds are in this molecule? 1, 2, 3, 4, 5, 6. Okay, that's really good. Got the same number in our list that we have in the molecule. The one last thing that I will emphasize after having drawn this species is that double bonds are not the same type of bonding for both of those lines. Double bonds are made of 1 sigma and 1 pi bond. The bonding in a double bond is different. There's a sigma bond that's on the axis of bonding, and there's a pi bond that's around the axis of bonding. How are we doing? I'm totally off my notes, so I want to make sure you're catching up with where we are. Gerardo, is there anything in the chat? Oh, sorry, Gerardo. Is there anything in the chat?
No, I think you're good. Although I was going to ask, you can't see that we're emoting, right? Like when we clap hands or give you thumbs up. Okay, then.
I'm not looking at you at all because you've all made yourself black boxes, and that doesn't help me keep my rhythm. Let's put it that way. But if you want to unmute yourselves and applaud at any time, it's completely welcome. I feel very alone over here, I have to admit. It's okay. I'll be okay. It's just a very different way to teach. I think you know that, because it's also a very different way to learn. Okay, I drew formaldehyde earlier. I want you all to take a practice. I want you to list all the bond types in this molecule. And I want you to list where do any non-bonding electrons live. I want you to go through this process. I'm going to give you 4 minutes to list all the bonds, potentially try to draw a picture of the bonding if you want to try to practice doing that. Where do all the electrons live? If you finish your list and your drawing and whatnot and you want some more time to practice, think about the next thought question also. So there's a thought question down here that's sort of thinking ahead to our next unit, which is thermochemistry. So if you have a moment, we can think about that one. We've been sitting here together for a really long time. I encourage you to get up and shake it out, stretch around a little bit. All right, does anybody need more time? It's fine if you do. Unmute yourself and let me know. If not, I'm going to keep moving. All right, I'm going to keep moving. How would I answer this problem? The first thing I'm going to do is ask myself, what's the hybridization of each non-hydrogen atom? Remember, hydrogens can't hybridize. They only have the s orbital, so all hydrogen is coming to us with is that s orbital. That's all it gets to use for bonding. So for carbon, I have 3 atoms attached and none lone pairs, which tells me I have a steric number of 3. If I have a steric number of 3, then carbon has to be sp2 hybridized. For oxygen, I have 1 atom attached. I have 2 lone pairs. So I also have a steric number of 3. And so oxygen is also going to be sp2 hybridized. sp2 meaning I need 3 hybrid orbitals. 1 s orbital is going into that mixer. 2 p orbitals are going into that mixer. And on the other side, I get 3 sp2 orbitals. So I'm going to start my picture by having my central atoms, carbon and oxygen. I understand there's a bond between them. There's actually 2 bonds between them. What types of bonds are they? Anytime you see a double bond, there is a sigma bond that forms on the axis of bonding. So this is sp2, this is sp2. That sigma bond is formed by hybrid orbitals overlapping. There's also a pi bond. Between carbon's p orbital and oxygen's p orbital. So far, if we're keeping score, we've got 1 sigma carbon oxygen that's formed by sp2s. We've got 1 pi carbon oxygen that's formed by p orbitals. Those are the 2 bonds that exist between carbon and oxygen. Okay, well, where else do electrons live? If something is sp2 hybridized, then there are 3 of those sp2 orbitals around that atom. On oxygen's side, those sp2 orbitals are going to hold those lone pairs, those 2 electron groups that are invisible. But they do live around that atom. They need to have a place to be, so they're living in those hybrid orbitals. For the carbon, there are 2 more bonds. between the sp2 orbitals of carbon and the s orbitals of hydrogen. So there are 2 lone pairs also in oxygen sp2 orbitals. Now, does my tally make sense? I've got 1, 2, 3, 4 bonds. I've got 1, 2, 3, 4 bonds. So my tally makes sense. I've got 2 lone pairs. I've got 2 lone pairs accounted for here. How we doing? I don't see the chat. Anybody let me know if there's something in the chat.
You're good.
Okay, we are gearing up for thermochemistry. Things are about to get a little crazy up in here. I want to think about that ahead of time. Thermochemistry relates to changes in energy that happen in chemical reactions. These changes in energy result from changes in bonding. A carbon-carbon single bond has an average bond energy of 347 kilojoules per mole. A carbon-carbon double bond has an average energy of 611 kilojoules per mole. Use what we've talked about today so far to explain why does a double bond not simply twice as energetic as a single bond. So if we were twice as energetic, we'd be 694 kilojoules per mole. If we simply took that carbon-carbon sigma bond and we multiplied it by 2, we'd get 694 kilojoules per mole, but instead we see a 611 kilojoules per mole. Why that difference? How can I explain that? I'm gonna let you think a minute. I want you to write down on your paper, why do you think there's this difference? If you're not sure, maybe go back and revisit some of the pictures we've been talking about.
Is it because of the overlapping?
I heard a mumble.
I said, can you hear me?
Now I can't.
Is it because of the overlapping of the bonds?
Tell me more. What do you
Well,
mean by
Does
overlap?
that mean like depending, well, as they become more complex structures, there's more overlapping or like perpendicularity, and I would assume that those energies are gonna like be pushing and pulling against each other, I guess. So that's why it's not an exact double. I don't know.
I think that there's elements of what you said that are right. I want to see if anybody else is thinking and maybe can add to that description. Don't be afraid to unmute yourself and try. It does have to do with overlap. That's a great word to use. But what about overlap? Be more descriptive about overlap. What types of overlap contribute to those types of bonds that are described?
Would it be like shielding is going on?
So shielding really relates to how attracted is a valence electron to its nucleus. So that's really thinking about within an atom, the atomic structure relationship. So this isn't really about shielding as much as it is how do we build the molecule in the first place? How do I build a carbon-carbon single bond? What overlaps to form a carbon-carbon single bond? What is a single bond? What's another name for single bond? Also starts with an S.
One S or S? S.
Starts with an S, ends with sigma. Sigma. Carbon-carbon single bond is a sigma bond. How do sigma bonds form? What overlaps? How do sigma bonds form? What overlaps?
Like an S and a P orbital?
In this bond list right here, what's overlapping to form the sigma bond? Not an S and a P orbital.
SP2?
Hybrid orbitals, sp2 orbitals. Those hybrid orbitals overlap. Where do they overlap? On the axis of bonding. Do you think that's really good overlap? Sure. It's so good that the bond allows for free rotation. So this atom can spin around and not be detached from the other atom. How is a pi bond formed? By the overlap of what?
2 p orbitals.
2 different p orbitals. How do they overlap? Around the axis of bonding. Do you think that's as constructive an overlap?
No.
Hiya! Hiya! Anytime I move, I lose my overlap. So is this interaction as strong as this interaction? No. So it's not simply twice the energy because the bonds are constructed in different ways. They're formed by the overlap of hybrid orbitals on the axis of bonding or the overlap of p orbitals around the axis of bonding. This one is much more sensitive, a bit weaker, and so that's why it's not twice as much. That's why it's a little less than twice as much. Okay. Trying to be aware of time. To explain this, I want you to think about how bonds form. Sigma bonds form by the overlap of what?
SP2.
I want to be more general. Starts with an H.
Hybrid.
Hybrid.
Hybrid orbitals. On the axis of bonding. Pi bonds form by the overlap of what?
P orbitals.
Beautiful. I love it. I was going to say starts with P, but that gives it all away. P orbitals. It starts and ends with P. Overlap of P orbitals around the axis of bonding. Since the overlap of p orbitals is less complete and more sensitive to rotation, pi bonds are a little less stabilizing or weaker than sigma. That's why it's not merely a double. So that overlap is less good. The strength of that bond is less strong. Excuse me. How we doing? Folks, I know this lecture is super boring. I get it. I'm trying to make it as animated as possible. I know this is a lot of concepts that it feels like it's being thrown at you. What I'm hoping to, or what I'm really deliberately trying to do, is scaffold this new knowledge on stuff that you're already familiar with. So this idea of steric number that you already know how to calculate, and now relating to that steric number to what type of hybridization you need to adopt. Okay, there's one last form of hybridization. Let's talk about sp hybridization. So the Lewis structure for acetylene is seen here. What's the steric number for carbon in this compound?
4?
1 or 2?
2.
Okay, I've heard 2 votes for 2. Heard 1 vote for 1. 1 vote for 4. Anybody want to take 3? Let's backtrack.
I
What
changed my vote.
type of hybridization are we?
SP
How many orbitals mix?
2.
2. So what should my steric number be?
It's
2.
2.
2. So how do I get a steric number of 2? Here's my carbon. How many atoms are attached to my carbon? 1, 2 atoms are attached to that carbon atom. So there are 2 atoms attached, none lone pairs, which gives me a steric number of 2, which means I need 2 hybrid orbitals. I need to mix 2 orbitals to make hybrid orbitals. Okay, I'm going to remind you, what did my neutral carbon look like? And then I'm going to ask you to put 1 s orbital and 1 p orbital in that blender and spit out and tell me, what does sp hybridization look like? Where are the electrons? What do you predict in terms of bonding of an sp hybridized carbon? Okay, I threw 2 orbitals in the blender. How many orbitals should I get out?
2.
2. Where should they be energetically? Same as same as S, same as P, somewhere in the middle.
In the middle.
Somewhere in the middle, closer to P, closer to S, or literally right in the middle.
Closer to P?
So since it's a 1-to-1 relationship,
Oh, never mind.
half
Half.
and half P. So I'm pretty much in the middle. So there's my 2 SPs. What are the other 2 orbitals on that sp hybridized carbon? They are p orbitals that didn't go into that blender. So the p orbitals that didn't go into the blender are the ones that had stuff in them. The p orbital that was empty went into that blender and got spit out into the SPs. So my remaining 2 valence electrons go in the SP. So what does this tell me about bonding? How many sigma bonds does an sp hybridized carbon want to form?
2.
You got it. I got 2 half-full hybrid orbitals. That means that carbon that is sp hybridized wants to form 2 sigma bonds. What else does carbon that's sp hybridized like to form?
2 pi bonds.
You got it. Perfect. Those p orbitals are screaming, I want to overlap with another one of you. Please help me, complete me, make me into a pi bond. So carbon that is sp hybridized still has 4 bonds. 2 of them are sigma bonds and 2 of them are pi bonds. Of course, I'm going to ask you to draw the picture. Who can name one bonding interaction that these 2 carbons have and what orbitals overlap to form it? What's one type of bond in this molecule?
Sigma bond?
Sure, there's a sigma bond. What? Name any of them. Between
SP to SP? Between the carbons?
Great, beautiful. There is an SP-SP carbon-carbon sigma bond. Right there on the axis of bonding. Thank you. All right, Gerardo, you're off the hook. You don't get to answer anymore today. You've helped me too many times. I need a new friend. What's another bonding interaction that these carbons are experiencing?
A sigma bond, carbon sp to hydrogen, or to hydrogen s. And there's two of those.
Great. Thank you, Emily. You're off the hook. No more answers from you today. Need a new friend. What's another bonding interaction that's in this molecule?
There's a pi bond between the two carbons.
Tell me more, Kate. What overlaps to form it?
Is it 2p orbitals?
That's right, 2p orbitals. You got it. Take me home, someone. What's one more bonding interaction that happens in this molecule? Is that it? Do I have total in my list, 3 bonds. I should put 2 right here. So 2, 3, 4 bonds. How many bonds are in this picture? 1, 2, 3, 4, 5 bonds are in this picture. What's the 5th bond?
It's another pi bond.
You got it, Kino. Another pi bond. I have 2 pi bonds. Well, how do I draw that? Here's where it gets awkward. What's the angle between 2p orbitals around a carbon atom? If I tell you there's 3 p orbitals, there's a px, a py, and a pz, what's the angle between p orbitals on a carbon atom? What's the angle between the x and the y-axis?
Is it 120?
It's 90. So I have 90-degree angles between my axes. So what I'm going to draw sort of hurts to draw, but it's like there's a p orbital coming out at you and then going into the paper. Your book does a little bit better picture of this than I do. They have graphics editors. So I have 2 p orbitals. They are 90 degrees from each other. They are both overlapping around the axis of bonding. They are both overlapping around the axis of bonding. They are 90 degrees from one another. So a triple bond, we've now unlocked to say, is 1 sigma bond and 2 pi bonds. 1 sigma bond and 2 pi bonds. Both pi bonds are formed by the overlap of p orbitals. The p orbitals are 90 degrees from each other. Okay, important to note, I have only talked to you about SP, SP2, and SP3 hybridization. I will not discuss DSP3 and D2SP3, which are the theoretical constructs of how we form steric numbers 5 and 6. I'm not talking about that. Ain't nobody got time for that. So we're going to focus on SP, SP2, and SP3. So any atom that has a steric number of 2, 3, or 4, you should be able to explain with hybridization. Steric number of 2, I need 2 hybrid orbitals, so I'm SP. Steric number of 3, I have 3 hybrid orbitals, so I'm SP2. Steric number of 4, I need 4 hybrid orbitals, so I'm SP3. You do not need to do the higher order bonding models. All right, I've got a little bit of time left. I want to bring it all together. I want you to, I'm going to give you the Lewis structure. I want you to list all the bond types that are in this compound. And I want you to draw me a picture of this compound with all the bonding and non-bonding electrons drawn into it, and the types of orbitals that hold those electrons labeled. Excuse me. Try not to look back, only look forward. I'll give you 4 minutes.
Are we supposed to be doing this on the whiteboard or just in our notes?
I was just thinking of that. I was like, I didn't tell him to put it on the whiteboard. Why don't we put it on the whiteboard? That's a fun activity. I will stop sharing and I will look at what you got. So once you got a picture you're happy with, go to the whiteboard, put it up there and save it. I want to look at what you got. One more minute. If you've got a drawing you're happy with, go ahead and put it on your whiteboard and don't forget to click save. How we doing? We need any more time? We've had about 4 minutes so far. I'm seeing some good pictures. I like what I'm seeing. Ooh, somebody even adopted my color scheme. There's no bonus points for that, but flattery is nice. Has everybody had enough time to think about the problem? I don't want to spoil it for you if you still need a little bit of time. All right, I'm hearing nothing. I'm gonna start broadcasting again. Okay. Who can tell me one bonding interaction in this molecule? Somebody who hasn't talked yet. I saw a lot of good things on your papers. Don't all jump at once. I got 4 bonds.
A sigma bond from C to N, SP.
Thanks for bailing out your peers, Kate. Actually, I'm just realizing that I've lost basically most of the class. There's like 5 people left on this call. So tell the people who I told you were off the hook that you're off the hook, then nobody's going to answer me. So let's keep going. I'm going to try not to get mad. What is another interaction? Got 3 more to go.
An S.
There's a
That's
there's a sigma between hydrogen and carbon, right?
You got it. So SP and S. Great. What else? Thank you, whoever said that. I didn't recognize that voice.
Jason Dow.
Yes.
Thanks, Jason. What's another one? I got 2 more. They're the same type. There's my hint.
2 pi bonds between C and C and N.
You got it. I got 2 pi bonds. These are p orbitals. So one is in the plane of the paper and one is into and out of the plane of the paper. Is that it? Is that the only place electrons live?
There's the lone pair, but that's where I get confused.
So that lone pair, Kate, lives in a hybrid orbital. It lives in an sp orbital. So steric number of nitrogen is 1 atom attached plus 1 lone pair. That means there are 2 groups that need to be accommodated, which means the nitrogen is also sp hybridized.
Got it.
So nitrogen alone looks like this. Nitrogen sp looks like what? This is good practice. Nitrogen sp, what are the orbitals for sp hybridization for nitrogen? How many sp orbitals are there? 2. How many p orbitals didn't get mixed? 2. So I'm going to leave those 2 alone with their electron in it. And then the remaining 3 go into the hybrid sp orbitals. So by my color scheme, here's where my pi bonds are, 2 pi bonds. Here's where my sigma is, 1 sigma bond. And here's my lone pair, 1 lone pair. How we doing?
Got it. Cool.
Okay, I know this was a heavy day. I know this was a heavy day. Go do the practice. Flex these muscles that you've built. The practice should be very straightforward following this lecture. I mean, you might want to give your brain a little time to relax. We've been working for a really long time. So maybe try the practice tonight or tomorrow while it's still fresh on your mind. I just want to give you a preamble to where we're going. The last lecture of this week brings it all together. Whereas we had atomic level diagrams, which is what we were doing here. These are atomic orbitals. And how do they mix to form new hybrid orbitals that form molecules? Well, the last piece of that is molecular orbitals. So how do we build energy diagrams that explain the differences in energy of bonding in molecules? So this is the asynchronous lecture piece that's still in your week 8 module. This piece will not be on exam 2. Through page 14 will be on exam 2. Anybody have any questions before I let you go today?
Can you repeat what you just last said? It kind of cut out.
Yeah. So up through page 14 is what'll be on your assessment. There's one more lecture this week. Whereas we've been doing atomic orbitals and now thinking about hybrid orbitals, the last piece of chapter 11 is to think about how you build molecules with those orbitals. So the bonding orbitals that you create are called molecular orbitals. And so this piece is really talking about diagrams that show the relative energies of orbitals that hold the electrons that are in the molecules. So when these things overlap, they form new molecular orbitals. Sigma bonding, pi bonding, sigma antibonding, pi antibonding, and non-bonding. And so this won't be on your exam. It is heavily related to all the things we've been talking about. It will be on exam 3.
And then regarding our exam, we're not going to get a chart, a Vesper chart, right? That's all going to have to be memorized?
That is a thought process you have to be able to go through on your own. You're not getting a chart.
Fair enough.
All right, friends. Thanks for your hard work. It's week 8. You're halfway there. Halfway!
Yay.
Counting or anything. I'm totally counting at this point. So,
Thank you.
what?
Thank you.
Thank you.
Thank
Yeah,
you.
thanks.
You all are amazing. I would fail college if I were doing it the way you're having to do it right now. So I don't really know how I would be you right now.
Don't worry, I am failing college the way I'm doing it right now, so we're all good.
You're rocking it out. I believe in you all, and I want to thank you for your hard work. Please keep letting me know if things are unclear, or if you don't understand due dates, or you can't find something. Everything should be on Gradescope. Kate, I got your earlier email, so I've made sure everything is live. Sorry, I forgot to publish it.
Not a big deal. Yeah, I already submitted that, so it's all there.
All right.
So, all right. Thanks. You're doing awesome. Even in this whole situation.
Yeah, you've got like the tenacity of a stand-up comment. Today was just not the best room.
Oh, it's not funny. Today is not funny at all.
Yeah.
I wanted to say I picked up my library book from the library and it was really easy and it went well.
Wait, what are you reading?
I'm reading Being Mortal by Gawande.
Oh, I've got a lot of people who liked that one.
I'm in a health policy and management class and we talk about him constantly. So I was like, oh, sweet, double dip.
So I'm going to go learn about this guy who keeps getting quoted.
Exactly, yeah.
Cool.
Yeah, I got mine through the Contra Costa through the Walnut Creek branch, and it was awesome too. It was so easy. So
Wait, well, I want you guys to, you gals and guys, to take the moments that you need to not, like, to let your brain wander in a different space and go check out that book.
that's what my book is all about.
Oh, good. So you understand the importance of what I'm saying, which is,
Mine is the nature fix, so that's like the whole.
oh my gosh, I love that book. That's like,
Yeah, I'm really enjoying it. So that's a good plus.
Kate's book is all about the research that tells you why it's important to go be in nature. And what is restorative about nature.
Yeah, it's awesome.
Cool. Oh,
right.
I'll read that after.
It's called the
Yeah.
nature.
It's actually it pointed out some things about what nature is compared to when you go to the park in the city. It's not the same as actually getting out.
And
And I
like,
didn't realize that.
my favorite fact from that book is like there are 20 to 30% of people for whom nature does nothing. I feel really sorry for those people.
The whole reason I'm doing this is I'm one of those people. I get out there and I'm like amazed by everything I see. So, at this point in my life, going back and going through all of this, that's the whole reason.
It's super great. I love that book.